Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. These lectures cover the measures of dispersion, range, variance, and standard deviation. Again, normally we use the range, variance, and standard deviation to measure the dispersion of a data set. So we're going to learn how to determine the range of a data set, also how to determine the variance, and a standard deviation of population and a sample. Also, we're going to learn how to use the empirical rule and also Chebychev's theorem to interpret standard deviation. So we start with the range. The range is the difference between the largest and the smallest data values. So again, if we have a data set, we look for the smallest value and the largest value. The difference between the two will be our range. So an example here says we should calculate the range of the following data set consisting of the numbers of times the television channel was changed in a 1 hour time span. So we have a data set of a 4, 6, 16, 9, 24, 8, 12, and 1. So we are going to look for the largest value. In this case, the largest value will be 24, and the smallest value will be 1. So the difference of 24 and 1 will give us the range. Again, to find the range, we find the difference between the largest and the smallest value. Next, we go to absolute deviation or the mean absolute deviation. Now, when we have a sample mean absolute deviation, is given by the following formula. Again, MAD stands for mean absolute deviation. And to find the mean absolute deviation, it will be the sum, absolute sum of each value minus the mean divided by the sample size. Again, here we are looking for the sample mean absolute deviation. So each value in the data set minus the average value of the data set, absolute. It's the sum of all divided by the sample size. So let's see an example here. Suppose we have 6 people participated in 1,000 meter run. Their times measured in minutes are given below. Now to find the mean time, it will be 5 plus 10 plus 9 plus 11 plus 9 plus 7 divided by 6. The sample size is 6. We have 6 students. So the mean will be 8.5. Now to find the mean absolute deviation, the first thing we need to find is the mean. Then we are going to subtract the mean from each value. So to find the deviation, it will be each value minus the mean. Our first value was 5, so 5 minus 8.5. The second value was 10, 10 minus 8.5. Next value is 9, 9 minus 8.5. So again, we subtract the mean from each value. Here we have 6 values. Then we find the absolute deviation. Now the absolute deviation, actually that's why we call it absolute. Absolute value means always the answer will be positive. So the absolute deviation of 5 minus 8.5 will be 3.5. We know 5 minus 8.5 will give us minus 3.5 because 8.5 is greater than 5. But again, here we are looking for the absolute deviation. So the difference of all these values will be positive. Then we add all the values together. If we remember, the formula is the sum of the absolute difference between each value and the mean of the data set. So when we add all together, we get 10.0. Now the percentage of the total deviation, basically what we do, we multiply each value here by 100. So we get 35%, 15%, 0.5%, 25. 2.5 times 100 will give us 25%. So the total always will give us 100%. Next, our question said we should calculate the mean absolute deviation. So we are going to divide the absolute sum of the difference, which we have 10, by the sample size. In this case, we have 6 times. So 10.0 divided by 6. And that will give us 1.7. So 1.7 minutes will be our mean absolute deviation. Now here we say that on average, the points are 1.7 units from the mean. So always the mean absolute deviation gives us some value that is a measure from the mean. So since again, the answer was 1.7 minutes, it means 1.7 each on average, it will be 1.7 minutes from the mean, unit from the mean. So here we should note that the contribution to the sum of the deviation is proportional to the size of the deviation. So if one absolute deviation is twice as large as another, it will contribute twice as much to the value of the statistics. So for example here, let's compare the data point 7, which is 1.5 unit from the mean, to the data point 11, which is 2.5 unit from the mean. Now in this case, the percentage contribution to the total deviation will be 15% for 7 and 25% for 11. So let's see, here we say a variability measure in which each data value contributes proportionally to its distance from the mean seems reasonable. So here we say the mean absolute deviation is sensitive to outliers. And we shall see, and as we mentioned in the previous lectures, outline means a very small value comparing to the rest of the values, or a very large value comparing to the rest of the values. So for example, if we look at our data set here, we can see we have 5, 10, 9, 11, 9, 7. Now, an outline data can be 100 minutes or 200. 200 is too large comparing to the rest of the values here. Or we may have a very small value, 0.011 minutes, which is too small comparing to the minimum 5 to 0.011. So with the mean absolute deviation, since we are finding the difference of each value and the mean, then we add all together absolutely. We can see that if we have a very small or very large value, it will have effect on the value of the MAD. So let's see an example here. You can see now we have 5, 10, 9, 11, 9, 7, which is nice values. They are within their range. Let's say the smallest is 5, the highest is 11. But now we have 200. So we can see that the 200, we will say, is an outline. Comparing 200 to the rest of the value, the difference is very big. So this result will tell us the outline will have effect on, again, the MAD value or the mean absolute deviation value. In this case, since the outline value is very big, the mean absolute deviation also will be very big. So we find the deviation as we did previously, the difference of the mean with each, we can see that even the mean value is very big now, because we are going to add all the value, divide by 7, comparing to previously. So here we have our total value to be 328.3 divided by 7. And we can see previously we have 1.7 minutes. Now we have 46.9 because the outline value, very large value. So here now we will say that the mean absolute deviation changes dramatically, increasing to 46.9. Therefore, the mean absolute deviation is very sensitive to outlines. The same thing when we are finding the measures of central tendency, we say the media doesn't affect the outline, whether it's very small or very large, but the mean value always have effect when we have outline data that are very large or very small, it will change. And the same, since here also, we are looking for the mean before we find the value for the mean absolute deviation, surely it's going to have, the outline will have effect on the data. So here we say the mean absolute deviation is very intuitive measure of variation, but it's not used very often. So that will take us next to the most important values that we use to measure dispersions or variations in the data set, and that is variance and standard deviation. So what is a variance? Here we see a variance of a data set containing the complete set of population data is given by the following. So this time, instead of the mean absolute deviation, we find the difference of each value. We make it absolute addition sum. Now, with variance, to get rid of the negative values, we square. So we find the difference of each value and the mean, then we square, then we find the sum of all the squares difference. So here also, it's the same concept as the mean absolute deviation, but this is more better. Then we divide by the sample size, or in this case, population. So we divide by the population size. Normally, if we are looking for the variance and our data set is sample, we will divide by the sample size minus 1. If it's a population, we divide by the whole population size. So we say the variance of a data set containing a sample data, again, is the same, the difference of each value and the mean, all squared, the sum, divided by n minus 1 for the sample size. Now let's see an example here. Given the following times in minutes of 6 persons running 1,000 meter course, complete the sample variance. So this is a sample data set. So first, again, we look for the mean. We say the mean is 8.5. Add all the value, divide by 6. Then after we get the mean, we are going to subtract it from each value, which we did here, deviation. But this time we are going to find square deviation, not absolute deviation. So the result that we have, we square each one. For example, 5 minus 8.5 give us negative 3.5. Negative 3.5 square will give us 12.25. Same thing, the next value, 10 minus 8.5. The answer is 1.5. 1.5 square will give us 2.25. So after we finish, we add all the values. That's the square deviation. We sum all, we get 23.5. Then we divide by the sample minus the sample size minus 1. So here the sample size is 6. We divide by 5. So our variance will give us 4.7 square minutes. Now we say here that the average square deviation of the data is 4.7 square minutes. So the phrase square minutes in the last sentences may seem a bit odd because no one carries out transaction in square minutes or square dollars or square tons. So it's very difficult to interpret the significance of the measurement in this form. So this will lead us to find the standard deviation. So to find the standard deviation, that will be the square root of the variance. So in this case, again, instead of saying in minutes, square minutes, we are going to say in minutes. So let's see the standard deviation. Now, the standard deviation is also a measure of how much a data varies around the mean. And this is the most common unit or value that we use to measure the variation of data sets. So for example, if we find out that the data and the standard deviation equal to 0, it means all the values are the same. If the standard deviation is very small, it means the values are very close to each other. The variations is very small. If the standard deviation is very big, it means the values are widespread or the variation is large. So again, these are the properties of standard deviation. A standard deviation is always non-negative. Why? Because variance is always non-negative also. It is 0 only if all the data values are exactly the same. So you only get a standard deviation of 0 if all your values are the same in the data set. Also, the standard deviation can increase dramatically if there are one or more outlines in the data set. Same thing applies to variance, and the same thing applying to MAD, mean absolute deviation. Why? Because we are using the mean value. Remember, we are going to subtract the mean from each value. And since we know that always the mean is prompt to outline, if we are using it, then it's going to be prompt to any items we are looking for that use the mean. So these are the empirical rule, the properties, and we may cover this more detail when we start probability distributions, concept, normal distribution, etc. So here we say that if a distribution of a data is a bell shape, that's also called the normal distribution. We'll talk about this more when we cover probabilities. Then about 68% of the data should lie within one standard deviation. And also 95% of the data should lie within two standard deviation. And 99.7% of the data should lie within three standard. This is a property for, again, empirical rule. 68% always lie between one standard deviation of the mean. 95% of the data should lie within two standard deviation of the mean. Then 99.7% of the data should lie within three standard deviation. If, again, the distribution is a bell shape or a normal distribution. So let's see an example here. Suppose a group of high technology stocks has an average earnings per share of $6.26 with a standard deviation of 1.37. Now, if the data process or the data possess a bell shape distribution, which interval contains 68% of the earning, which interval contains 95% of the earnings? So again, the key word is that the distribution of the data is a bell shape or normal distribution. So we know 68% is one standard deviation, and then 95% will be two standard deviation. So using the 1 sigma rule, we will capture 68% of the observation because the standard deviation is 1.37. So 1 times 1.37 will give me 1.37. So 68% will be on one standard deviation. So it will be 6.27 plus or minus 1.36. So 60% of the distribution will lie between 4.89 to 7.63. Now let's look for 95. 95% means two standard deviation. So with 95% of the earnings, we are going to get 2 times the standard deviation, which is 1.37. So that will give us, when we check the interval here, -2 times 1.37 from the mean, and positive 2 times 1.37, which means adding to the mean. That will give us the interval of 3.52 and 9.0 because it's two standard deviation, 95%. So it will be 2 times 1.37 from 6.26. That will give us 3.52. Then 2 times 1.37, adding to 6.26, that will give us 9.0. So that will be the interval between, again, 3.52 to 9.50. So the last section is we're going to talk about the Chebyshev's theorem. This is the theory, again, we use a lot for the standard to, again, get the standard deviation together. So here we say the proportion of any data set lying within the K standard deviation of the mean is at least the formula given here, 1 minus 1 over K squared. K should be greater than 1. The K is the number of standard deviations. So for example, here we say if K equal to 2, then at least 75% of the data values lines at what we have here, 1 minus 1 over 2 square equal to 3. So that gives us 3/4. 3/4 is 75%. So that will be lying within 2 standard deviation of the mean. K is how many standard deviation for any data set. Now, if the k is equal to 3, then we get 1 minus 1 over 3 square, which gave us roughly 88.9% of the data values. So this means k is the number of standard deviation. So we will say that the data values lie within 3 standard deviation of the mean for any data set. And the Chebychev's theory is applied to any data set. So the distribution can be bell-shaped or not a bell-shaped, any type of distribution. But the standard empirical rule is only for the normal distribution. Again, that's for the bell-shaped or normal distribution. So example given here, they say the age distribution histogram for New Jersey in 2007 shown in the graph. So the age is the horizontal axis, which we will call the x-axis, the age. Vertical is the population in 1,000 for New Jersey population by age. Now here we say the mean of the data is given to us to be 37.2, while the standard deviation also is given to be 22. What can we conclude with Chebychev's theory using k equal to 2? So k equal to 2, since we know k is equal to 2, we can make an interpretation here saying that we are going to find the interval where the population will fall within these 2 standard deviation. So the solution here will be, because we are interested in k equal to 2, we will look at the values for 2 standard deviation above and below the mean. So the 2 standard deviation above the mean, we have mu plus 2 standard deviation. Remember, mean is given to us to be 37.2. The k is 2 and the standard deviation is 22. Let's make sure. So from the question, we can see standard deviation is 22, the mean is 37.2. So if k is 2, then it will be, again, 37.2 plus or minus 2 times 22. And that's what we have here, 37. And the answer here, we have 81.2. And 2 standard below the mean will be minus now. So the answer will be negative 6.8. So here, because age cannot be negative, we have a natural boundary. So we'll consider this as 0. Again, this information is about age. So the age, there's 2 standard deviation will be from 0 to 81.2, because we know age cannot be negative value. So therefore, by Chebychev's theory, we can say that at least 75% of the population of New Jersey is between 0 and 81.2. Why we say 75%? Because we remember Chebychev's theory is 1 minus 1 over k square. So we get 1 minus 1 over 2 square, and that will give us 0.75. So that will be 75%. So that will be the conclusion of these lectures. Again, these lectures, our main concern is learning to measure dispersion of a data set. So if a sample data or a population data is given to us, we want to know how the data varies. Is they're almost the same or not? So in this case, the key measurement will be standard deviation. But again, as we can see, we went through how we can also use the mean absolute deviation. We can also use the variance. We can use the range, but this all will not give us exact good values. The standard deviation were good. So again, wish everybody the best, and we meet in class. Thank you.